All right. I think we are live now. I'm gonna do the thing where I just like wait a tiny bit to make sure. And Twitch is showing me ads, which means it thinks that I've started. And I don't see anything from YouTube yet. Wait a tiny little bit. Resize some windows, make sure I can see the chat. Okay, it says I'm streaming. I haven't changed the key. Okay, oh, there we go. It just took a really long time to start for some reason. Good morning, everybody. You can see me probably, or at least see my screen and hear me. Welcome back. I mentioned last Friday, if you were here, that I probably wouldn't be here today because I was going to be traveling. I did not do the traveling because Seattle got a bunch of snow and every flight out of SeaTac that I could have taken was canceled. So I'm here and streaming with you guys, and I've been stuck in the house for a while, and yeah, glad to have some interaction on the internet. And we are finishing up maybe finishing up. I think we're going to finish the paper today, but I guess we'll see. The BERT paper, which we have been reading through. This is part 4. The previous 3 parts are in the Kaggle reading group playlist. I try to be really good about putting stuff in playlists, so let me know if I miss stuff. And the Kaggle YouTube channel. That was the second thing I was going to say. So let's jump right back into it. And last week, we got all the way through. So we've talked about the model specification, the tasks. We talked about all of the different tasks that we were, that the system was evaluated on. And we also talked about how the system did better because it's a machine learning paper, and that's what the results section of stuff you want to get published looks like. Although again, this has not been published. I wouldn't necessarily say it's not been peer-reviewed because I think a lot of people have read it and talked about it online, but just something to keep in mind. All right, and so as I remember last week, we found a lot of the tasks really compelling and interesting, and then the named entity recognition and situations with adversarial generations data sets were we didn't get a lot of information on, so had some questions there. And also the way that tokenization was handled for the named entity recognition was a little bit interesting. Not something I have seen previously, let me put it that way. And again, this is a good study. I don't necessarily think it's bad work, but I think it's useful to be like, oh, hey, there's something where you could have done something different, you know? One sec, I'm gonna blow my nose. All right, that should hopefully be better. It's certainly better for me. So the last part of the paper, and I believe this is the final section, and then probably 6 is going to be the conclusion, is Ablation Studies. So basically, they try taking something out and see how that affects the model. So it's not a theoretical explanation of why the model is better for a specific task or is better for a particular type of data, but it is an empirical investigation of what qualities of the model are contributing most to the performance on specific tasks. There was a really good question in... It was either the Kaggle forums or the Kaggle Noob Slack channel recently where someone was like, hey, what type of model is best for a specific problem? Will you say that switching from model, from like gradient boosting to XGBoost is always going to get you a benefit? And the answer is it's really hard to say. Partly because there hasn't been, there's been more done on random forest-based models, but there's not a lot of theoretical work on the, decision spaces that particular model types are better for. there's some, but there's not a whole lot of it. And this sort of empirical study where you just try a bunch of things and see what happens is sort of the current approach that's most common. The Answer to Life says, hey, just got back from a SWE interview, software engineer, which was pure fill, so I'm glad this reading is live now for a chill cooldown. I'm sorry that you had a bad interview. Yeah, interviewing is rough. Both for the interviews and the interviewees. So let's jump back in to the Ablation Studies, Section 5. Although we have demonstrated extremely strong empirical results, the results presented so far have not isolated the specific contributions from each aspect of the BERT framework. In this section, we perform ablation experiments over a number of facets in BERT in order to better understand their relative importance. So they're seeing which qualities of the model architecture are most affecting the output. Ooh, there's a seaplane. The snow has stopped now, so life is kicking back up. 5.1, effects of pre-training tasks. So if you remember, the BERT model is trained in an unsupervised way, so you just give it a lot of data and it notices patterns in the data, more or less. And then you take that model that's been trained in an unsupervised way and apply it to a supervised task, so some sort of classification. And they are looking at what different types of pre-training tasks do. So one of our core claims is that the deep bidirectionality of BERT, which is enabled by MaskLM language model pre-training, is the single most important improvement of BERT compared to previous work. To give evidence for this claim, we evaluate two new models which use the exact same pre-training data, fine-tuning scheme, and transformer hyperparameters as BERT base, so the smaller model that they used. So what are they doing here? So if you'll remember when we were reading previously, something that I suggested was that maybe the contribution of this work was actually the sort of the masked pre-training task. And here they're saying that it is not just the task itself, but the specific model architecture that they're using. So the deep bidirectionality of BERT, so the ability of the model to look in both ways, is enabled by the MaskLM pre-training. So are they using the same data, fine-tuning scheme, and transformer hyperparameters? Okay, so they're trying to train models using slightly different things. Sonyam says, quick question. This is the first paper I've read. Is it okay if I share my notes from the live stream as a Kaggle discussion for a feedback on my understanding? Yeah, absolutely. Also, this is quite a paper to jump into. One quality that papers in particular have is that they you can think of academic papers as turns in a conversation, right? So I'll say something and then my colleague will say something else, then I'll say something else, and we go back and forth. So there's this sort of assumption that you are familiar with the rest of the conversation. And that assumption is not present for things like textbooks or dissertations, where you get started not from sort of like the middle of the conversation, but you sort of are introduced to the topic and the relevant work. And there's a very abbreviated version of that in papers, but especially computational linguistics papers, just because they're so short, you don't get a lot of the background. So if you are starting with papers and you are very confused by them, that's not your failing. It's just you're coming into an ongoing conversation. And if you stick around enough and like read a lot of other papers, then it can sort of make more sense, and you'll get a better sense for sort of what's new in the conversation and what is something that people have covered previously and they're just referring back to. So anyway, that's just my little aside about reading scientific literature. Little coffee. Okay. So they have two new models that are training. One which has the masked linear model, so where you have words and you mask some of them, but don't have the next sentence prediction task for the pre-training. And then they have a second model which is trained using left to right LM rather than MLM. So this is, so in this case, we predict every input word and do not apply any masking. The left-only constraint was also applied at fine-tuning because we found it is always worse to pre-train with left-only context and fine-tune with bidirectional context. Additionally, this model was pre-trained without the NSP task. This is directly comparable to OpenAI GPT, but using our larger training dataset, our input representation, and our fine-tuning scheme. So this is a simpler version of what they did, and this is a slightly different version that's supposed to be more parallel to the OpenAI project. So Nam says, thanks. Oh. Ryan says, when reading these papers, you just have to act like you know what the words mean until you actually do. Basically. Or, I mean, you can look them up if you have, access to relevant materials. So the thing that I find interesting here is, so they're doing left to right language modeling, which is not super common these days. Well, let me think about it. For some things it is. Like, I don't think people generally use bidirectional language models for speech recognition. Although I guess you could, if you're sort of fine-tuning your hypotheses of what words are given your input features. But it's interesting that if you're pre-training only looking forward, basically, because we're talking about English here. Anarchy, Mellow, and Gabsense2 say hello. Hello, everybody. It's interesting that if you are trained only looking forward, then doing fine-tuning with forward and backwards looks is always worse. Interesting. Interesting. And then they use the same data set, input representation, and fine-tuning scheme. Results are presented in Table 5. We first examine the impact brought by the NSP task, next sentence prediction. We can see that removing NSP hurts performance significantly on QNLI, MNLI, and SQUAD. So these are natural language inference and then question answering task. These results demonstrate that our pre-training method is critical in obtaining the strong empirical results presented previously. If you are working at the sentence level, it looks like. Let's look at Table 5. Where's it at? Table 4? Nope. Table 5. Okay. So here are the data sets. Here are the different models that they looked at. So this is the one where the fine-tuning is done bidirectionally, and this is the same model where fine-tuning is done unidirectionally, so only looking forward. Didn't they say that it is always worse? Oh, it is always worse to pre-train with left-only context. But this one, it looks like it actually improved to do bidirectional tuning. I'm assuming that that's what this is. Oh, no, it's another layer. So, ablation over pre-training tasks using the BERT-based architecture. No NSP is trained without the next sentence prediction task, so that's this one. LTR and no NSP is trained as a left-to-right model. Left-to-right language model without the next sentence prediction, like OpenAI GPT. BiLSTM adds a randomly initialized BiLSTM on top of LTR plus no NSP model during fine-tuning. Sorry, that's me thinking, aren't you not supposed to do random initialization anymore? Isn't that a thing you're not supposed to do? LSTM, random initialization. Let's see, this is from 2017, so it might be a little, vintage. Random initialization. Random initialization of the network weights. Random initialization allows the networks to learn a good approximation for the function being learned. Oh, it's zero initialization you're not supposed to do, right? Because that can kill neurons, I think. But again, this is like empirical results I'm trying to dig out of the oatmeal. So jump in the chat if you're like, nope, that's not the one, Rachel. Okay, so the thing that they want us to get from this model is that, oh look, the model that they're telling us the best is the best and outperforms the rest of them, and that the next sentence prediction task is much better for some of the tasks and like slightly better for some of the other ones. So the answer to life says, yeah, it is zero initialization that you're not supposed to do. Okay, so random initialization is yes, zero initialization is no. I knew there was something about random initialization and not doing it. Okay. So they're suggesting that the next sentence prediction task is helpful for, looks like it's more helpful for sentence level tasks. The answer to life says, could be wrong, doubting my existence at the moment. Yeah, that's something I should look up later and make sure that I have the current understanding on. Next, we evaluate the impact of training bidirectional representation by comparing no NSP to LTR and no NSP. The LTR model performs worse than the MLM model on all tasks, with extremely large drops on MRPC and SQUAD. For SQUAD, it is intuitively clear that an LTR model will perform very poorly at span and token prediction, since the token-level hidden states have no right-side context. So there's no way looking to the right to see them. For MRPC, it is unclear whether... For MRPC is unclear, probably it is unclear, whether the poor performance is due to the small data size or the nature of the task. But we found this poor performance to be consistent across a full hyperparameter sweep with many random restarts. Ryan says, if you have zero initialization, you can't break symmetry. Gradient will be the same for all neurons. Random initialization is good. It has been shown to have a special kind of random, though. Keras has various initializers that help you be random in the right way. Thank you, Ryan. That's helpful. It's good to make sure that the things that I have in my head are real. I recently, for a long time, I'd sort of like filed mushrooms as under foods that are like all fat like avocado, and they are in fact very low fat and very high protein. So yeah, that's a good example of how you can think things that are wrong. And it's good to look them up. Okay. In order to make a good faith attempt at strengthening the LTR system, we added a randomly initialized, which is good, BiLSTM on top of it for fine tuning. This does significantly improve results on SQUAD, so this last one, but the results are still far worse than pre-trained bidirectional models. It also hurts performance on all 4 glue tasks. We recognize that it would also be possible to train a separate RTL and LTR models and represent each token as the concatenation of the 2 models, as Elmo does. However, this is twice as expensive as a single bidirectional model, and if you'll remember from what we talked about earlier, recurrent neural networks have slower training time because you have to do time step n before you can do time step n plus 1 because they are sequential. So taking twice as long for an RNN model in terms of training time is quite substantial. B, this is non-intuitive for text like question answering, since the RTL model would not be able to condition the answer on the question. And C, this is strictly less powerful than a deep bidirectional model, since a deep bidirectional model can choose to use either right or left context. Okay, this makes sense to me, and suggests why the bidirectional models that they are proposing might be more powerful than an LTR and RTL methods used together, which I believe they have a visualization of, if we scroll really far up here in the Elmo. So you can see there's one right to left and one left to right model, and then the final output is conditioned on both of those. So, Magpie says, lol, what? I'm not sure where I lost you, but you can, excuse me. pardon me, that you can feel free to ask a question. And I think I've gone too far. Where were we? Yes, okay. 5.2, effect of model size. In this section, we explore the effect of model size on fine-tuning task accuracy. We trained a number of BERT models with differing number of layers, hidden units, and attention heads, while otherwise using the same hyperparameters and training procedure as described previously. Results on selected glue tasks are shown in Table 6. How are those selected, I wonder, is the question that I have. In this table, we report the average dev set accuracy from 5 random restarts of fine-tuning. We can see that larger models lead to a strict accuracy improvement across all 4 datasets, even for MRPC, which only has 3,600 labeled training examples and is substantially different from the pre-training tasks. It is also perhaps surprising that we are able to achieve such significant improvements on top of models which are already quite large relative to the existing literature. For example, the largest transformer explored in Vaswani et al. Is L6, H equals 1024, A equals 16, with 100 million parameters for the encoder. And the largest transformer we have found in the literature is L64, H12, A2, with 235 million parameters. Al-Rafu et al. 2018. We can see that larger models lead to strict accuracy improvements across all 4 datasets. So basically they're saying bigger model better, even if you have very few training examples. By contrast, BERT base contains 110 million parameters and BERT large contains 340 million. So they're saying that their model is much bigger and also has better performance, and that it is a function of size. So as we... set our cups down on tilted surfaces. So as we increase the performance on some tasks increased. So okay, perplexity you want to be down. Yeah, LMPPL is the maxed language model perplexity of held out training data. So how surprising it is, basically, oh my gosh, I always get perplexity backwards. You can think of lower perplexity as being less surprised by the data you haven't seen yet, if that makes sense. So accuracy goes... Oh, wait, I see. So they're increasing L and decreasing A here, but you still see an improvement. Oh, thank gosh. Finally they have this. So L is the number of layers, H is hidden size, and A is the number of attention heads. Ankit says, I don't think the type of initialization affects too much. It should be random and not too large and not too small. I wonder if I'm hallucinating this paper, but I remember reading at some point about basing the initialization on the distribution of the training data. I don't know, maybe I'm making that up. I don't want to get too sidetracked. I do want to finish the paper today, and I also am going to blow my nose again, I'm sorry. I've just had a drippy nose for like 3 weeks now, and I'm done with it. Okay, so they've decreased the number of attention heads, but increased the number of layers. And when they increase both the number of layers and attention heads, we see further improvement. And that trend continues. So as your model gets bigger, your performance gets better, and there doesn't seem to be a ceiling to that they are claiming. Pointing out that their model, the BERT model, is the largest trained transformer that they could find in the literature at the time that they wrote this. It has been known for many years that increasing the model size will lead to continual improvements on large-scale tasks such as machine translation and language modeling, which is demonstrated by the language model perplexity of held-out training data shown in Table 6. However, we believe that this is the first work to demonstrate that scaling to extreme model sizes also leads to large improvements on very small-scale tasks, provided that the model has been sufficiently pre-trained. Interesting. Interesting. Okay, so section 5.3, effective number of training steps. Sorry, I don't think that this is super surprising, because like bigger models better is definitely something that we've seen a lot of, also for things like speech recognition, which has a language modeling component. But their suggestion is that the pre-training and fine-tuning means that even if you have very small, well, relatively small training data, bigger models are still going to be better. Although, I mean, at some point the model is too big, right? At some point it's just ridiculous and you've spent too much money and time on it when you could have been doing other stuff, and you are not getting increasing returns anymore. And I think that happens, you know, more quickly in situations outside of Kaggle competitions than it does in other ways. It's me says, hey Rachel, could you start something new on numerical data? Not right now, but yeah, if you've got a suggestion for a paper, we could work on a numerical paper next. I will have less background. Okay. Figure 4 presents MNLI dev accuracy after fine-tuning from a checkpoint that has been pre-trained for K steps. Okay, so this is just increasing training time, basically. This allows us to answer the following questions. 1, does BERT really need such a large amount of pre-training? 128,000 words per batch times 1,000,000 steps to achieve high fine-tuning accuracy. Yes. Answer. Yes, BERT base achieves almost a 1% additional accuracy on MNLI when trained on 1,000,000 steps compared to 500K steps. So I guess the question is, are you willing to wait that long for a 1% increase in accuracy? And the answer life says, ooh, surely Cybenko's paper? I don't think I'm familiar with this particular paper. Is it the approximation by superpositions of a sigmoidal function from 1989? It looks like I could do some signal processing, maybe. 2, does MLM pre-training converge slower than LTR pre-training, since only 15% of the words are predicted in each batch rather than every word? So the difference is that we have sentences, some of the words are hidden, we're trying to predict the hidden words rather than always trying to predict the next word. Answer. The MLN does converge slightly slower than the LTMR model. However, in terms of absolute accuracy, the MLM model begins to outperform the LTMR model almost immediately. The answer to life says, yes, basically proof that neural networks can compute any function. Ryan Scheffler says, paper cited 10K, that seems important. Yeah, we can give that a try. Oh, that's a lot of proofs. Oh, that's a lot of proofs. I'm gonna put that in the maybe section. I'll take a look at it. You guys know how good I am at saying math words out loud. Okay, so their argument, even though it converges more slowly because accuracy is higher, that doesn't matter, is the argument that they are making. Okay. 5.4, feature-based approach with BERT. All of the BERT model results presented so far have used the fine-tuning approach, where a simple classification layer is added to the pre-trained model, and all parameters are jointly fine-tuned on a downstream task. However, the feature-based approach, where fixed features are extracted from the pre-trained model, has certain advantages. First, not all NLP tasks can be easily represented by Oh, excuse me. Ugh. Pardon. Blah, 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 blah. Fixed features are good. Why? Not all NLP tasks can easily be represented by a transformer encoder architecture, and therefore require a task-specific model architecture to be added. Second, there are major computational benefits to being able to pre-compute an expensive representation of the training data once, and then run many experiments with less expensive models on top of that representation. So that's, basically the thing where you would use pre-trained word embeddings instead of training your own word embeddings every time. It's me says, why don't you start a new channel besides this to help beginners with data science, as you are very good in explaining things? That's an idea. One sec. I'm grabbing a sheet of paper. I shall think about it. Okay. And the other reason why you want to do the sort of the fine tuning is because you don't want to have to redesign and model architecture every single time you have a new type of task. So I think that's a big gain right there. If you were watching the live coding and saw how much we were struggling with Keras, I think minimizing that is a good goal. In this section, we will evaluate how well BERT performs on the feature-based approach by generating Elmo-like pre-trained contextual representation on the Connell 2003 NER task. To do this, we use the same input representations as in section 4.3, but use the activations from one or more layers without fine-tuning any parameters of BERT. These contextual embeddings are used as input to a randomly initialized 2-layer 768-dimensional BiLSTM before the classification layer. Same input representation as in section 4.3, but activations for one or more layers without any fine-tuning parameters. Contextual embeddings, okay, so the trained language model basically is being used as embeddings. So where you would put word embeddings to a randomly initialized 2-layer 768-dimensional BiLSTM before the classification layer. So basically you're using BERT in place of pre-trained word embeddings as the input to this BiLSTM. Results are shown in table 7. The best performing method is to concatenate the token representations from the top 4 hidden layers of the pre-trained transformer, which is only 0.3 F1 behind fine-tuning the entire model. This demonstrates that BERT is effective for both fine-tuning and feature-based approaches. Excuse me, sorry, I should be better about muting. Layers. Fine-tune all. So fine-tuning everything gets you a pretty good F1 on the development set. If you only use the first layer as the input, that's okay. If you use the second to last hidden layer as the input, that's also pretty good. And then if you sum the last 4 hidden, so your embedding would be 1 for each of your, would be a vector of length 1, then that does okay. And if you concatenate the last 4 hidden layers, so you have a longer embedding, a higher dimensional embedding, basically, that does even better and better than fine-tuning everything, which is a computational time savings. So that's interesting. So they're almost arguing that the pre-trained BERT models can be used as like I'm trying to think of a good metaphor. Like bread, I guess. Yeah, they're like bread. So either you can sort of take the bread and make a sandwich with it, or like an open-faced sandwich, or you can fine-tune it by like pulsing it down to breadcrumbs and putting it into bread pudding, or doing more manipulation of the original model, but that if you just sort of like take a slice of it, you can still do pretty well. Okay. Oh, that was the last part. Interesting. Conclusion. Recent empirical improvements due to transfer learning, with language models have demonstrated that rich, unsupervised pre-training is an integral part of many language understanding systems. In particular, these results will enable even low-resource tasks to benefit from very deep unidirectional architectures. Wait, what? No, this is a bidirectional architecture. One sec, sorry. Recent empirical improvements due to transfer learning with language models have just demonstrated that rich, unsupervised pre-training is an integral part of many language understandings. Okay, yes. In particular, these results enable even low-resource tasks to benefit from very deep unidirectional architectures. This is previous work. Okay, our major contribution is to further generalize these findings to deep bidirectional architectures, allowing the same pre-trained model to successfully tackle a broad set of NLP tasks. So rather than just looking ahead, so basically they're saying, hey, language models are good, lots of people use those. What if they were bidirectional? Oh, it turns out they're pretty good. Well, the empirical results are strong, in some cases surpassing human performance. That's a bold claim. Important future work is to investigate the linguistic phenomena that may or may not be captured by BERT. Okay. Ryan says, so they put the inputs through BERT and they took 4 internal activations and passed those into a BILSTM. Yes, I believe so. Abhishek says, why my Kaggle webpage doesn't open? Please give answer. Oh, that is hard to diagnose. I'm sorry. I would try different browsers, potentially. It could be blocked by your local internet provider, or if you're doing stuff from work, it could be blocked by your work firewall. Also, maybe check your internet, make sure your internet's good. I don't know. I'm sorry. It's really hard to, it's a very vague question. Although I understand that it is frustrating. Okay. So basically it works good. We have no idea why or what for. Well, that's not true. That's not true. They do have a little bit of idea why. Oh, hey, Jeremy Howard. Are there footnotes? There are not footnotes. Interesting. So the thing that I find helpful about this section of the paper is this table, which I think helps to demonstrate the importance of the bidirectionality, except I think this model was also not trained on masks. Was it? Do you guys remember? Let me see. Oh, Misties. Okay, sorry about that. The LTR model, how did you train it? Model was trained left to right rather than using a masked language model. So the reason that you couldn't use a masked language model with a traditional left to right model is because it's always predicting the next word, and if your next word is or like masked, you wouldn't be able to get the information out. So you need some sort of attentional model that's attending over the whole sequence in order for masking to actually be helpful. So I think when I said earlier that the greatest so yes, the masked language modeling task is very helpful, but at the same time, you need to have something that's not a traditional language modeling architecture in order to capture it. Okay, so this is making more sense to me. I think I have a better idea of the particular things that are important about this particular paper. Oh, there was something I wanted to look at. So they were talking about the other very large, when they were talking about the size, and they were saying that, excuse me, that bigger is always better. They talked about this other really large model, Alrafu, character level language modeling with deeper self-attention. So I just wanted to take a little peek at this paper and see what it was all about. Oh, I have definitely read it previously. LSTM and other RNN variants have shown strong performance on character level language modeling. These models are typically trained using truncated backpropagation through time, and it is common to assume that their success stems from their ability to remember long-term contexts. So basically, as you feed sequence into an LSTM, it can choose to remember things that it thinks are important and forget things that it thinks are not important through the use of something called a forget gate, which is, I know we're going pretty deep into RNN land right now, and this is not what the other paper is about. In this paper, we show that a deep 64-layer transformer model with fixed context outperforms RNN variants by a large margin, achieving state-of-the-art on two popular benchmarks, 1.13 bits per character on text 8 and 1.8 on IngWiki 8. And bits per character is a measure of entropy, which is the inverse of perplexity. I always get them backwards. 100% of the time I get them backwards, which means that I know what they are. I just don't know which one's which. To get good results at this depth, we show that it is important to add auxiliary losses both at intermediate network layers and intermediate sequence positions. Interesting. And this was last revised on December 2018. Was this published anywhere? Let's see. Archive link, ResearchGate, GitHub, Reddit, open review citing it, Semantic Scholar. So Semantic Scholar isn't a publishing venue, but it does have information on it, and archive. Okay, so this paper also hasn't been peer reviewed, which is something to be aware of. And I mean, in a perfect world, every time you cite a paper, you have read the paper and have a thorough understanding of it, and you know, have already done your own quality checks to make sure that it is something that you are that is work that you either believe in and express the belief, or work that you have found, you know, areas for improvement in, and you are doing that improvement, and you you know, that's what your paper is that you're improving their work and saying, oh, hey, the authors didn't think of this, or they didn't try this, or we tried the thing that they did, except if you have a slightly different data set, it doesn't work as well, and here's why we think that is, or something like that. So ideally, the authors of this paper have read this paper very closely, but again, it hasn't been peer reviewed, which is, you know, something to keep in mind. All right, and it's been cited by Transformer XL, language modeling, BERT, adaptive input representations for neural language modeling, practical text classifications with large pre-trained language models, self-attention latent space between. Sorry, I'm just reading paper titles now. Okay, so yeah, I don't think I have much else to say about this paper right now. It's definitely, so BERT has definitely been popular and gaining in popularity as a method of you know, doing language modeling, and also they're suggesting you can use sort of a language model approach to replace embeddings, which makes sense because embeddings are basically a lower dimensional representation of co-occurrence, and BERT has information on co-occurrence and also something like syntactic relatedness due to the fact that it has attention over time. So yeah. Yeah, I'm interested to play around with it. There's a co-reference resolution competition right now that's going on that I think some people have done BERT approaches for, so that might be some place to look for it. Actually, let's see. .com/competitions. And I think I saw a kernel with BERT, but I could be wrong. No, the gendered pronoun resolution one is the one that I was thinking of. If we look at kernels, NLTK, Spacey, GenSim, text data, research summary, sentences with highlight, word embeddings. Ryan Chesler says, everyone is just using a feature-based approach so far because it's hard. It is definitely hard. Co-reference resolution is difficult, to say the least. Yeah, interesting. But this could be a potential application for BERT. For sure, because you can get because the data looks like, we played around a little bit with this last time. So the data looks like you have the full text and then the pronoun and then the character offset from the first character of the pronoun. And then A and B are the potential words that the pronoun could be referring to. So you could do a full text. So you could do sort of this architecture. Scroll here, where you have the full text here. And then a SEP, and then, so I guess the CLS here would be, the classification would be either A, B, or neither, and then you'd have the full text, and then the separation, and then I guess the first word, and then a separation, and then the second word. Yeah, Ryan says, we don't have enough data to truly train a model. Need to do something on OntoNote's bigger data set and then transfer it over. Keeping in mind that OntoNotes has a worse gender representation problem. As it just has a lot of male entities in it, and the particular problem that this competition is trying to resolve is that co-reference resolution is significantly better for male entities, for male pronouns, than it is for female and other pronouns. So Vinay says, sometimes I get the error, data loader worker is killed by signal, bus error. What should I do? I have no idea. I would ask that on the product feedback forms. What was I saying? Okay, so you might do, I'm trying to think how I would create the BERT embeddings for this. So I think I would do, because you definitely want the full text, and then part of the text is the specific thing that you're looking at. Let's see, so sentence pair classification tasks, single sentence classification tasks, question answering tasks, and then single sentence tagging tasks. So I guess maybe the thing that would be most relevant would be the single sentence tagging tasks. And then I guess you'd have like, I guess what I would probably do is I'd have a placeholder for token A, a placeholder for token B, and then a placeholder for the pronoun, and I'd have the classification, whether it was A, B, or the pronoun, and then the sentence with the placeholder, and then a separation, and then the pronoun, the A, and then separation, then B, and then separation, then the pronoun, I guess. Yeah, it's a little bit tricky. And then I guess you could also get like the word level output, because I guess this is, so this is a named entity recognition task, where your tags are at the sentence level, at the word level, sorry, as opposed to a co-reference resolution tasks where you have multiple words and you're trying to draw an edge between them, basically. Ryan says, but it would be a better metric model overall, which is the actual metric the competition is being run on. Yeah, if you have overall performance increase, then that would be good, but you don't know what the gender balance of the So if you have a better model overall, but you're getting that improvement by increasing your performance on the most common classes and decreasing your performance on minority classes, which will in most cases get you an improvement in model accuracy, then given that you don't know which classes will be minority and majority in the actual testing data, it is possible that training on a larger data set with an imbalance will actually get you worse output on the final evaluation set, even though it got you better input in the initial training page. Does that make sense? So because the classes in the original set are imbalanced and you know that you're going to get a different class balance, but you don't know what the balance is going to be, you might end up shooting yourself in the foot with a larger data set. Hopefully not. But yeah, I agree. It is a relatively small data set. Fortunately, it's in English, and we have a lot of data in English, as it turns out. Yeah, so I'm not entirely sure how I would structure this to go into a this particular task to go into a BERT model, but that's my sort of current approach that I think I would take. Yeah. I think the other thing that I would do is I would see if I couldn't find a larger data set. So onto notes, I think, is one of the bigger ones, but if I could find even sort of like semantic web data sets that might be relevant, that might work. You might have to do a little bit of data augmentation and labeling, and you'd have to point people towards the data set in the forums as well. That's in the rules. So you can augment with data as much as you like, as long as you tell people about it in the forums, and you don't have to pay for it, and it's public. So okay. So I think that's pretty much all I have to say about BERT. I hope this was helpful for you guys. I'm definitely getting a lot of requests for a non-NLP paper next. Some questions about numerical data, some suggestions about this is the paper, by the way, that was mentioned in the chat. This God, was this Mimo typed? This paper, approximation of superpositions of a sigmoidal function. This is a lot of math, y'all. Why do we say sigma is discriminatory if we're a measure sigmas in the set of mi's? I don't know what these letters mean. Maybe it's mentioned up here. Probably it's not. This does seem like a useful paper. I feel like I at least already have a fairly good intuition about why neural nets can approximate functions, and we actually talked about that on the channel a while ago as well, when we were reading the actually one of the NLP textbooks goes into it. So the what's it called? One sec, let me pull it up really quick. So the playlist, so in the Kaggle reading group playlist, it is in the neural networks and neural language models reading group thing, and I think it's this one where we talk about why. Yeah. So it's this particular video is where we talk about the neural networks and neural language models. Video is where we talk about why you can approximate any function with a neural network of a certain size. So that might be. So reading this paper might be redundant, and also it looks intimidating. And Ryan says, I saw this paper where they were trying to extract the training data by probing the neural network. So you could probably specify what sentences, so you could find specifically what sentences were passed to the model. Yeah, there's some really interesting sort of spaces in copyright law where a neural network trained on a text data set can in theory be used to reconstruct that text data set. So if you are including copyrighted text in your training data, does that mean that your neural network has copyrighted text in it and is covered by copyright law? Question mark. But yeah, I'll do some thinking. Feel free to recommend me papers on Twitter or Kaggle. I am RCTATMAN on Twitter. I try to be pretty responsive, and we'll pick a paper for next week. Yeah, I don't think I'd had any big requests. I got a lot of requests for the BERT paper, which is why we did it. So I'll spend some time thinking on it. Okay. Thanks for joining me today as we wrapped up the BERT paper. I hope you found this helpful. I definitely feel like I have a better understanding of what's going on in this paper. And I don't think this is the last we will see of BERT and friends, for sure. I will be back on Friday. I'll be doing live coding. I haven't decided what I'm going to be doing yet. Maybe we'll work on a BERT implementation. We'll see. And I definitely heard you guys about doing more beginner focused videos, and I will definitely think about that. That is on my radar now. So that's all I had for you today. Thanks for joining. I hope you found it helpful, and we will meet again next Wednesday, same time, 9 a.m. Pacific, and I will be live streaming on Friday at 4 p.m. Pacific. Bye.